Okay, here are the answers from your homework last night. Although I just noticed, I looked at the YouTube video and there's only 4 views. So, unless you guys were having a viewing party last night and you all went to each other's house or something, then that tells me not very many people probably did this. So, it's not good. I'm going back to my bad mood ways now. But anyway, if you did, here are the answers. I'm not really going to go over them, just you can check your answers, and yeah, I don't know what to do when no one does stuff, so. And there's 11 and 13 and 14. You can rewind it if you need more time. Just notice on 14, these are intervals. So like, I put a bracket there, but because it includes -1, put a parenthesis there because it doesn't include 0 or any of those. So that is that. I think I might have made it, I didn't rewatch it, but I might have made an error when I was in that last video. I was talking about how for a function to be continuous, you have to be able to draw it without lifting your pen up off the paper. And this is kind of stupid. I don't know if this will come up again, but that's technically incorrect. If I look at, like, here's y equals 1 over x. If I look at the interval from like here to here, we could say that this is discontinuous because there's a vertical asymptote there, right? But this is known as a continuous function. You might be like, well, that's stupid. It's not continuous. There's a gap there. And I agree. But for a function to be known as a continuous function, it only has to be continuous on every point in its domain. So, x equals 0 is not in the domain of this function, and that's the only point where it's not continuous. Therefore, this is known as a continuous function. Weird, I know. So, yeah, it doesn't have to be continuous on every interval, just on the points that are in its domain. Polynomial functions, that's an n, are always continuous. And I know there's at least one person going, well, what's a polynomial function? That's anything like x to the whatever plus 2x to the whatever plus blah 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 blah. Just a long string of x to the whatever power, 3rd, 4th, 5th, 6th, whatever, who cares? Just a long string of them. Those are always continuous. There's not going to be any jumps or gaps or breaks. But all of our other ones, like rational functions, like that's a rational function, right? Rationals are fractions. Any kind of rational, like x squared over x, anything with a fraction in it, or any exponential functions or logs, or any of our trig functions like sine, cosine, tangent, any radicals like the square root of x, just the square root of x. Those are all continuous at every point in their domain only. I know it's weird. So like that, square root of x is known as a continuous function, even though there's nothing over here, because those points aren't in the domain of that. I'm giving you one homework problem on that, and then we're not going to talk about it again unless it comes up in March. Okay? Good deal. Alright, the rest of this is better. Let's see, where's my notes? What I want. So I said we're going to talk about removable discontinuities. Removable. Continuities. I don't even know how you'd spell that. Oh, that's good. This happens when, let's say we've got a function y equals f of x, and I don't know what this function looks like, but it doesn't matter. It goes, woo, does something, and then there's a hole there, and then it continues on its happy journey. So let's say this hole is like at 1, 2, 3, 4, 2, 3. So there's a hole there. That's a discontinuity, and I mentioned in the other video that's known as a removable discontinuity, because all we have to do, let's say here's our function y equals f of x. To remove that discontinuity, we basically just turn this into a piecewise function. We say, all right, we'll have y equals f of x, whatever this is, whenever x does not equal 4. So we'll say, okay, we're only going to use this whenever x does not equal 4. Because there's a hole there anyway, so why would we want to include that point in there? But then we'll say, okay, when x equals 4, if I want to fill in that hole, I'll just say when x equals 4, let my new piecewise function equal, in this case, 3. So if I do that, when x equals 4, y is 3, that basically just fills in that hole, and we have removed the discontinuity by adding this little stipulation down here. So we use the regular function when x doesn't equal 4, but we'll use 3 when x does equal 4. And that's how you remove a discontinuity. And this is known as the extended function, I guess. Meaning we added stuff to it to remove some discontinuities. I'll do a better example of that right now that's not just y equals f of x. So, an actual real thing here. Let's see. Let's say we got y equals x to the third minus x squared minus 2x over x squared minus 4. So we got a rational function, and we'll first decide if it's always continuous, and if there's any discontinuities, we're gonna write an extended function to remove the discontinuities. So we can do this a couple of different ways. Let's look at a graph of it first. I think I've already got mine typed. Oh, nope, I don't. So we got x to the third. Oops, I better put that in parentheses on the top. A graph. Whoops, I just want a regular graph. Oh, I got my window all messed up here. Zoom 6. There we go. Looks like we got a vertical asymptote here, probably at -2, right? Because if I plug in -2 squared, I get 4 on bottom. 4 minus 4 is 0 on bottom. Can't have that. That's where I get my vertical asymptote. This is a discontinuity, but it's not removable. Oh, I forgot to talk about that on that last one. In order to be removable, the function has to have the limit on either side in either direction has to approach the same thing. It's like in this case, our hole here, if I took the limit as x approached 4 from the right, I got the same answer as if I took the limit as x approached 4 from the left. If you have something like this, where you got something coming up and you got a hole, but then if it jumps, so that's 2, the limit as x approaches 2 from the left is different than as x approaches 2 from the right. That's not a removable discontinuity. You can't just plug in a number and fill in the hole. Same thing if you have a vertical asymptote. You can't just magically fill in this gap here. There's nothing you can do. The limit on from the right is different from the limit on the left. So that's not removable. But there should be another discontinuity here. Because if you look at this, you can probably think of another point for x that you can plug in that'll create a hole. I mean, when x is 2, shouldn't there be a hole there? But I don't see anything on the graph. It looks like it just goes right through there. And that's because our graphing calculators aren't capable of showing this. If I were to zoom way in right there on 2, whatever. So I don't like using the zoom in function because it takes forever. Like if I do zoom and go zoom in, it gives you a little cursor and you have to select the point to zoom in on. So I'll be like, oh, when x is 2 or 1, I can't even select 2. It's 1.91 or 2.12. I'll go there. There, that's close enough. Hit zoom in and it'll zoom in there. Still looks continuous, and I can sit here and do this all day. Like, it's still on zoom in. Like, if I just keep hitting enter, it'll keep zooming in, and I just adjust my little cursor to be closer to where I want it. Oops, and then I hit a wrong button and it messes up. But that's okay, because it sucks, and you can do that all day, and it doesn't work. Let's look at a table. Oh, my table to start it. Oh, I might as well go 2, because that's where I want to look. And if I leave my change in my table big, I won't see anything magic here. I'll just see an error at 2. Oh, hey, that's because it doesn't work. There is a hole there. But I want to know what value is it approaching. And if I just look at this table, I can't see anything. I just see it goes from 2/3, 1.07, and then error, and then some other random crap. And I really don't notice anything. If I made my change in my table a lot smaller, like I better start at 2 and go by 0.001 or something like that. Now it's pretty easy to see as I get really close to 2. These are getting really close to 1.5. And if I go on the other side of it, yeah, it looks like I'm getting really close to 1.5. So that's a way to see it on a table. That my point should probably be 2, 1.5 right there. Let's go back to the graph, and I'll zoom right in on 2, 1.5. But I'm not going to use zoom in, because like I said, zoom in sucks. It takes forever. So now that I've got it narrowed down to what I want to see, I'll go to my window. Yeah, and it's all messed up right now. So I'll go like on my X, I'll go from 1.99 and to 2.01, and I'll go by 0.01s or something like that. That'll just give me, my whole screen will just be from 1.99 to 2.01, and on my Y I'll go from 1.49 to 1.51. I'll go by 0.01s. So that's just going to give me that zoomed way in on that one little spot, and we'll see if it shows a hole. Oh, hey, finally. See, there's a tiny little gap there where there's nothing. The calculator just can't make it small enough because it's infinitely small. I mean, the further you zoom in, the smaller you could make the gap, because you could go 1.499, or I guess on the x-axis you could go 1.99999999999, but as soon as you get to 2, there's nothing. But as soon as you get to 2.00000000001, then there's something again. So that's why it graphically sucks. So anyway, we know our discontinuity is at 2, and we know it's removable because, well, looking at the graph, my calculator forgot what it was doing. But looking at, oh, I cleared it. Dang it. Looking at the graph, we saw that the limit on either side was the same. There was just a gap there, right? That's the calculator doesn't draw an open circle, but if it did, that's what it would have looked like. There was a hole there. So we can fill in that hole if we can figure out what it was approaching. And we looked at the table and we saw that when x was 2, y was really close to 1.5. And that actually is going to be the answer, but there's yet another way to do it if we just look at the function. If we can factor these and cancel out some stuff, we'll see if we can get that. I don't know what's going to happen here. This is interesting. So factoring the top, I think they all have an x in common, so I'll pull an x, and I'll have x squared minus x minus 2. Bottom, difference of two squares, x plus 2, x minus 2. On top, hopefully that's still factorable. X, let's see. X and x. multiply to negative 2, add to negative 1. I think that's negative 2 plus 1. And on bottom, we got still x plus 2, x minus 2. Hallelujah, look what happened. The x minus 2's cancel, and I'm left with x times x plus 1 over x plus 2. Well, so now what's happening as x approaches 2, well, if I plug it in, so if I just take the limit as x approaches 2 of this thing, or just plug it in, which I'll get 2 times 2 plus 1 over 2 plus 2. 2 plus 1 is 3. 3 times 2 is 6 over 4, which is 3/2, which is 1.5. And that's what the table was showing us. So we want this function, when x equals 2, we want y to be equal to 1.5. So when the directions say, give a formula for the extended function that is continuous at the indicated point, as you'll have to do on these problems, they actually tell you where the discontinuity is. You don't have to look for it. Well, like on 25, it's at x equals negative 3, so you go to negative 3, figure out what y needs to be so that you can fill in the hole. Here, ours was at 2, we figured out y needed to be 1.5, so we need to fill in the hole. So my answer is just this. I just say y equals, I'm going to turn it into a piecewise. I'm going to go, it's x to the third minus x squared minus 2x over x squared minus 4. It can be equal to that whenever x does not equal 2. But then when x does equal 2, I just want it to be equal to 1/2. Or not 1/2, 1.5 or 3/2. That's what we found. That, if I make it a piecewise, it fills in the gap there. The other one, right, the vertical asymptote part, we can't remove that. That's always going to be there. But that one was removable, and we've done it by turning it into a piecewise and saying let it equal 3/2 at x equals 2. So that is that. So some of your homework's going to ask, like 19, it asks to look for discontinuities and see which ones are removable. But you can just kind of think about it. That one's no calculator. Maybe draw yourself a little sketch of the graph. It doesn't have to be perfect. Figure out if it will have discontinuities. It might not. It might just, the whole thing might be continuous. And if it is, figure out how to remove them if they are removable. You can do 15 and 16 now, the ones I scratched off from yesterday. Like what value should be assigned to f of 2 to make the extended function continuous at x equals 2. So I'm saying if you want if you want it to be continuous right here at x equals 2, what value do you need to assign to y? Which that one's pretty easy. Let's see, I think that's it. I'm not forgetting anything. Oh, all right. So hopefully by the time class rolls around, those 4 views will have gone up to 13 views. Giving you some quick review problems. So there's those. Don't forget about your quiz tomorrow. And don't whine and tell me, oh, you gave us homework on different stuff when we have a quiz tomorrow that we had to study for on others. Yeah, welcome to a real class where it's not so easy. So have fun with this. This video is only 20 minutes, so you should have lots of time to work on this in class or study for your quiz, or maybe, let's say, go back and watch the first video. That'd be stupid. You're supposed to watch them in order. I don't know. See you tomorrow.